Let's discuss real zeros of polynomials. Before we get to the real zeros, though, let's start with rational zeros. And we're going to start with this polynomial. P of x equals x cubed plus 13x squared plus 56x plus 80. And I'd like to find the zeros. Well, without any tools, this would be quite cumbersome. Is 1 a 0? Is 2 a 0? Is 17 a 0? Well, we could eliminate 1 because we know that if you substitute 1 into this function, it won't add up to 0. In fact, you can look at this and see that no matter what positive number we'd put in there, we wouldn't have something that adds up to 0. So we can look at this particular problem and tell our zeros are going to be negative. But still, I don't know what number to try. -1, -5, -11. But what if I gave you a hint? Let me give you this information. I'm going to tell you that -4 is a 0. Could you find all the remaining zeros of this polynomial? Well, by my telling you -4 is a 0, that means that P of -4 equals 0. And in particular, if we did synthetic division here, and I use my coefficients 1, 13, 56, and 80, I'm guaranteed to have a 0 here. So let's do the division. We bring down our 1, we multiply and add, multiply and add, multiply and add, and there is our remainder of 0. So in fact, we know that P of x equals x plus 4 times, remember these are the coefficients of our other factor, x squared plus 9x plus 20. I don't remember if I made it clear what our task is. We're going to do two things: find all the rational zeros and factor. Once we have it boiled down to a quadratic, we're home free. We can use our strategies for factoring a quadratic expression, and if it didn't factor over the integers, we could use other strategies as well. But we know how to factor that. We'll bring down our x plus 4. You can use whatever strategy you have for factoring trinomials. I use trial and error, so I know my x squared gets broken up into x and x. 20 has possibilities of 1 times 20, 2 times 10, or 4 times 5. But we know a 4 and a 5 will work to give us that 9 in the middle. We need pluses in both places. And it'd be a little bit nicer if we wrote this as P of x equals x plus 4 squared times x plus 5. So we have our initial polynomial in factored form, and we could state the zeros. Remember, zeros are just numbers. So the zeros are -4 from this factor, or from these factors, and a -5. And of course, we could talk about the multiplicity. -4 has multiplicity 2, and -5 has multiplicity 1. But here's the issue. I gave you this information that -4 was a 0. That's what got us on our way. What if we didn't have that? And before we get to the answer to that question, let me show you something else. Let's reverse a process. Let's suppose we know the zeros. So the zeros of a particular polynomial are 3, -2, and 2/5. We could determine what the polynomial is based on this. We don't necessarily know what the leading coefficient would be, but we know if 3 is a 0, that x minus 3 would be a factor. And if negative 2 is a 0, then x plus 2 would be a factor. And let's see, if 2/5 is a 0, then we could have a factor that looks like 5x minus 2, right? If you have that as your factor, you set that equal to 0, you would get that particular 0. So this is one possibility for a polynomial with these zeros. Coefficient here could be a 1 or a 17, but I'm not worried about that. I want to show you something else. Let's multiply this out. If you multiply these two binomials together, you would get x squared minus x minus 6. And we're still going to multiply it by 5x minus 2. Now I'm just going to do the multiplication and give you the result, but you could take time to multiply it out if you'd like. But the result when you multiply those together is 5x cubed minus 7x squared minus 28x plus 12. And here's the point that I want to make. There's a relationship between this constant here and our zeros. In particular, notice that this 12 right here is the product of this 3, this 2, and this 2. Comes from these. And if we look at the leading coefficient, where did it come from? Well, it came from the product of 1 times 1 times 5. In other words, it came from this 1, and the 5. So there's a relationship between the numerators of the zeros and the constant, and the denominators of the zeros and the leading coefficient. Now, I haven't proven anything. I just wanted you to see that relationship. But it suggests what's called the rational zeros theorem. And let me show you what that is. The rational zeros theorem says this. We'll read it and then we'll boil it down. It says if you have a polynomial that has integer coefficients, then every rational zero of that polynomial is of the form p over q, where p is a factor of the constant and q is a factor of the leading coefficient. So the numerator of the rational zero must be a factor of the constant, and the denominator needs to be a factor of the leading coefficient. So let's see that with a particular example. Let's just state all possible rational zeros based on the rational zeros theorem for this particular polynomial. We'll let p of x equal 3x to the 7th minus 5x cubed plus x squared plus 15. So based on our rational zeros theorem, the possible rational zeros need to be of this form. A factor of the constant over the factor of a constant over the factor of the leading coefficient. And that's what you hear people say, P over Q. But in particular, let's list those possible numbers. Factors of the constant. The factors of 15 are 1, 3, 5, and 15. And the factors of 3, and I'm talking about integer factors, are 1 and 3. And of course, any of those ratios could be positive or negative. So let's just list the possible rational zeros. And any combination of a number in the numerator divided by a number in the denominator. So that list would be 1 over 1, 3 over 1, and let's put a plus or minus in front of each of these. 5 over 1, 15 over 1, and all of those numbers over 3. 1 over 3, 3 over 3. I'm about to write 3 over 3, but then I realize that's equivalent to 1, so it's just a duplicate, and I don't need to write it. And then we have 5 over 3. And last, 15 over 3, but that's equal to 5, and again, that would be a duplicate. So the possible rational zeros for this particular polynomial is listed right here. Now you would have to test, how many is that? 12 numbers, but that's better than an infinite number of possibilities. We have it boiled down to this particular list. Now there is no guarantee that any of these are actually zeros. The guarantee is if there is a rational zero, that it must be on this list. So let's do a problem. This one will say, find all rational zeros and write in factored form. So let's start with our list. So the possible rational zeros. Right? Factors of the numerator, or excuse me, factors of the constant over factors of the leading coefficients. So plus or minus, factors of 14 are 1, 2, 7, and 14. Factors of 2 are 1 and 2. So possible rational zeros would be on this list. 1 over 1, 2 over 1, 7 over 1, 14 over 1, 1 over 2, 2 over 2, that's a duplicate of this number, 7 over 2, and 14 over 2, which is a duplicate of that number. So here is our list that we begin with. The possible rational zeros for this polynomial are listed here. So we're going to take them one at a time and figure out which are actual zeros for this polynomial. Now we can do direct substitution and see if it gives us a 0, or we could use synthetic division and determine whether the remainder is 0. I often do a combination of those things. If direct substitution seems straightforward, I would do that. If the numbers get uglier, I'd probably use synthetic division. So for example, if I were finding P of 1, I'm testing to see if 1 is a 0. I could pop that into that polynomial pretty easily. 2 times 1 cubed, and you could do this in your head. Minus 9 times 1 squared, minus 33 times 1, minus 14. And I don't really even care what that number is. I care that it's not equal to 0, so I move on. I could put negative 1 in. 2 times negative 1 cubed, minus 9 times negative 1 squared, minus 33 times negative 1, minus 14. And do the arithmetic. What do I get? I have negative 2 minus 9 plus 33 minus 14. Again, don't know what it is, but it's not 0, so I would move on. And I just chose these numbers to test first because those were the easiest. I could have chosen negative 1/2 or positive 14, but I usually start with the ones that are easier. Now I'm moving on. We know that neither 1 nor negative 1 are zeros of this polynomial, so I'm going to move on to 2. And at this point, maybe I'll try synthetic division rather than direct substitution. My coefficients are 2, negative 9, negative 33, negative 14. Bring down my 2, multiply, and then add, multiply, and then add, multiply, and then add. It's not a 0, right? Because we had a remainder. So sometimes it takes you a little bit of work to get to it. Let's see, where do we at now? We've tried 1, -1, 2. Let's try -2. So our coefficients are 2, -9, -33, and -14. Bring down my 2, multiply and add, multiply and add, multiply and add, and we have found one. So we have found that -2 is a 0. We know that means that x plus 2 is a factor. So I like to write where I am so far. We know these are the coefficients of our other factor. So P of x equals x plus 2 times the polynomial that has these as coefficients, 2x squared minus 13x minus 7. And again, we have it boiled down to a quadratic. And then when that happens, we're home free. So we can factor that the way we normally factor trinomials. I'm going to just use my trial and error. I have 2x and x. Let's see, it's 7 and a 1 with a minus here and a plus here. Sorry, I'm writing this kind of tiny. But we have it factored now. Once you get it boiled down to a quadratic, often it's pretty quick to finish. The question said to write in factored form. We have that done, but we haven't stated the zeros. It specifically asked us to list those. Remember, zeros are numbers. Zeros are the numbers that would make any of these factors 0. So we'd have -2, which we had just found. The number that makes this factor 0 is -1/2. And the number that makes this factor 0 is 7. And notice the -1/2 and the 7 were also on this list. Let's do another one. I often look to see if we can factor using our traditional strategies before I drag out the rational zeros theorem. This one, I don't see anything I can do besides my rational zeros theorem. So let's get started. So our possible rational zeros. Any number that is a factor of 10 over a number that is a factor of 1. That's kind of nice. So the possible rational zeros are plus or minus 1, 2, 5, and 10. And we can start with any number we like. Notice that if you pop 1 in, and again, you may be able to do this in your head, you'd have 1 plus 1 minus 15 plus 23 minus 10. Can you see that that would be a -25 here, and a 23 and a 1 and a 1 is a positive 25. So a -25 and a positive 25. So I can tell that P of 1 equals 0. And if you can't tell, it's no big deal. You can try synthetic division or write out the direct substitution. So I'm trying 1 first, and we have 1, 1, -15, 23, and -10. And I begin my synthetic division. Bring down the first number and multiply and add and continue that process. And as expected, we had a 0 here. So now I like to write where I am so far. I have P of x equals x minus 1 times x squared plus 2x minus 13 let's see. Oh, this is x cubed. When we started with x to the fourth, we know this will begin with 1 degree lower than that. This was a 4, so this would be x cubed, and x squared, and x to the first, and plus 10, right? This is our remainder. This is our constant. There's our coefficient of our x term, x squared, and x cubed. And I always look at this to see if I can factor by grouping or some other strategy. I don't see anything there, so we continue the process using our rational zeros theorem, but now we're working on this. And just because one worked already doesn't mean it can't work again. For example, notice if we pop 1 in right here, it would equal 0. 1 in this polynomial would give you a 0. So we're going to do it again with our synthetic division, again with the coefficients from this polynomial. So we have 1, 2, negative 13, and 10. And we do our synthetic division. And there's our remainder 0. So we have x minus 1 as a factor again. So we have p of x equals this x minus 1 times another x minus 1. So we'll just write x minus 1 squared times x squared plus 3x minus 10. And this one now isn't too bad to factor using our trinomial factoring strategies. And we would have x plus 5 times x minus 2. So there's the factorization. And again, pay attention to what the directions are. I didn't write them here, but it was find all the zeros and write in factored form. So the zeros for this one are 1. Let me write this one next. I don't know why I'd write it next. We'll write this one. Negative 5 and 2. And notice this is a polynomial that you could graph if you needed to. Right? Now that you know the zeros, you know the multiplicity, you could graph this polynomial. Let's move on. Let's do another one. The directions have changed just slightly. The directions say find all real zeros. So now we're not restricted to the rational numbers, but we often start with that because it's a good starting place. But first, I always look to see if I can factor this using my traditional strategies, like factoring by grouping. This one isn't going to work, so we are back to our rational zeros theorem. So our possible rational zeros are any factors of 12 over any factors of 1. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So, a few to roll through to get to the result. Right? But again, we can do direct substitution of 1. 1 minus 5 plus 2 plus 12 is not going to give us 0. Similarly, you might be able to pop negative 1 in your head into the polynomial and determine whether it equals 0 or not. If you put in negative 1 here, you'd have negative 1, and then a negative 5, and a negative 2, and a positive 12, and that wouldn't work either. It wouldn't give us 0. If you can't see that, do direct substitution or your synthetic division. Turns out 2 isn't going to work either. Negative 2 isn't going to work. I just want to cut to the chase so that we can see the next piece I wanted to point out on this particular problem. You'd probably try 2 and negative 2 next. What will ultimately work is the 3, so let's get there. We have 1, negative 5, 2, and 12. Bring down my 1, multiply and add, multiply and add, multiply and add. There's my remainder 0. So my polynomial would be x minus 3 times x squared minus 2x minus 4. Now here's where this one is different than the previous examples. You can try to factor this, but it doesn't factor over the integers, right? If you tried to do this and look for the factorization, you wouldn't get very far. 1 and 4 doesn't work, 2 and 2 doesn't work. So that strategy just doesn't work. But remember, zeros are any number that makes the polynomial equal to 0. So once we get here, we set each factor equal to 0. Once you have factored all you can with respect to the integers, you set each factor equal to 0. Well, that's the 3 we already had. But on this one, x squared minus 2x minus 4 equals 0. If we find the solution to this equation, we will have other zeros for this. You can use quadratic formula or completing the square. I'm going to use completing the square because the leading coefficient is 1 and that's even. So we'll add 4. Take half of 2, it's 1. 1 squared is 1, so we'll add 1 to both sides. We have a nice perfect square here. Take the square root of both sides and add 1. So we get x equals 1 plus or minus the square root of 5. So our zeros for this particular problem are 3, 1 plus the square root of 5, and 1 minus the square root of 5. And we have all 3 zeros for this polynomial. Notice these 2 aren't on the list. That's because they're not rational. This is only the list of possible rational zeros. These 2 are irrational. Let's do one more. Often people forget to think about their other strategies that they have. Once they learn the rational zeros theorem, they want to use it for every problem. If you looked at the possible rational zeros for this problem, it's not a problem. We could list them plus or minus 1, 2, 5, and 10, right? Factors of 10 over 1. And what I see happen frequently is people roll through all of those, plus or minus 1, they try them, don't work. Nor do 2 and negative 2, and 5 and negative 5 don't work, and 10 and negative 10 don't work. And so then what people do is try them again. Well, if they don't work the first time, they're not going to work the second time either. And it turns out this problem is factorable using our other strategies. This particular problem we could factor using our trinomial strategies, or the strategies we use when factoring trinomials. I'd use trial and error for this one. We have x squared and x squared. 10 factors into 5 and 2. And we need a minus on both. And notice the product of these 2 binomials is this trinomial. Neither of these are factorable over the integers, but as we always do, once we have it factored as far as we can, we set each factor equal to 0 to find our zeros. So we have x squared equals 5, and we have x squared equals 2. So x equals plus or minus the square root of 5, and x equals plus or minus the square root of 2. So we do have 4 zeros for this particular problem, and they are square root of 5 and negative square root of 5, positive square root of 2, and negative square root of 2. So don't forget about your traditional strategies of factoring, your strategies for factoring trinomials, and sometimes you'll see that some problems will factor by grouping. Just don't forget those.